Alright, let's continue our discussion on atomic structure by talking about nuclear forces and nuclear binding energy. Now, within the nucleus, there are two primary forces that are going on. The first is the electric force, and this is actually a repulsive force between the positively charged protons in the nucleus. And it shouldn't be surprising that this is a repulsive force because you remember, like charges repel. Now, the fact that this is a repulsive force means that this interaction is actually trying to break the nucleus apart. And that's not what we want, so that means if we're able to form stable nuclei, there must be another force that is an attractive force. And that force is the strong nuclear force. You don't need to know much about how this force works for the MCAT, but you should know that this is an attractive force between the protons and neutrons in a nucleus. And when you have stable nuclei, this strong nuclear force is going to be stronger than the electric force. Okay, so now let's talk about the mass defect. The mass defect is a very interesting phenomenon that is best illustrated with this diagram. On the scale, you're going to see on one side, we have 4 individual nucleons, 2 protons and 2 neutrons. On the other side, we have the same 4 nucleons, but just fused together to form a helium nucleus. And what's very interesting is that you can see the mass of the nucleus is less than the sum of the masses of the individual nucleons. So that means when you form a nucleus, you lose mass. And that loss of mass is what is referred to as the mass defect. And as it turns out, when mass is lost, you also release energy at the same time. And you can calculate the amount of energy that's released using Einstein's famous equation, E equals mc squared, which shows us that the more mass that is lost, the more energy we release. Okay. So this means that this process of forming a nucleus is an exothermic process because we're releasing energy. If you consider the reverse process of taking a nucleus and separating it into individual nucleons, that has to be an endothermic process that requires energy. And as it turns out, that amount of energy required to separate a nucleus into individual protons and neutrons, we refer to that as the nuclear binding energy. And as we just mentioned, this is always going to be a positive value because separating a nucleus is always going to be an endothermic process. Okay. Now, while the nuclear binding energy is always a positive value, it turns out that different atoms, their nuclei have different amounts of nuclear binding energy per nucleon. What this means is that some nuclei are held together more tightly than others. And this is important because in nuclear reactions, if your products have more nuclear binding energy than your reactants, you're able to release energy. And we can see this if we take a look at this diagram here of a nuclear binding energy curve. This graph shows the amount of nuclear binding energy per nucleon in all the atoms of the periodic table. And what you can see is that elemental iron has the most nuclear binding energy per nucleon. So that means if you go up in mass or decrease in mass from iron, that nuclei are held together less tightly with less energy. And that actually explains why we're able to release energy in both nuclear fusion, where we take smaller atoms and fuse them together to form larger ones, and nuclear fission, where we take larger atoms and we split them into smaller ones. Now, in order for nuclear fusion to release energy, you must start with atoms with nuclei smaller than iron. And that's because they have less nuclear binding energy per nucleon than iron. And for instance, you could take 2 hydrogen atoms and you can fuse them together to form a helium atom. The helium nucleus has more nuclear binding energy per nucleon than the hydrogens. So in total, our products will have more nuclear binding energy than our reactants, so this ends up being an exothermic process. You can do the same thing in nuclear fission. If you start with an atom that is larger than iron, so for instance, we can take uranium and we can split that into smaller atoms like krypton, barium, and actually a few neutrons. And at the same time, our products have more nuclear binding energy than our reactants, so this process is also exothermic.